Welcome to another advanced Unity game dev tutorial. So today there's not a lot to explain. We want to move 100,000 objects. In order to do this, we need some special shaders. We need one that supports GPU instancing, and we need a compute shader to calculate all the positions and rotations of our objects. In order to avoid data transfer between the GPU and the CPU, we also will use graphics buffers or compute buffers. So the first thing you want to do is to create a simple test scene where you can move around your objects. So you have like a big plane of sand, and I have some fog in the background and a hook that you can move around with the input. And the main camera that just follows this hook. It's some very simple scripts. You surely know how to do them. And if not, you can ask ChatGPT. You also want to create a low poly model that is going to be used with our instancing shader. So let's create that by going to create shader, unlit shader, and in my case I'm calling it fish shader, and then I'm going to open this file. So in order for any instancing to work in Unity, we first need to include the Unity instancing file, and then we need to add a new shader variant, which is called multi-compile instancing. Now we need to tell Unity to fill in the information for each vertex, and from the vertex stage we can transfer the instance ID also to the fragment stage. So the keyword, the macro is called vertex input instance ID, and we will add it to both the vertex information and the fragment information. Now we need to fill up the data actually, which we'll do in the vertex and the fragment stage. In the vertex stage it's called Unity setup instance ID. You call it like this. And then we transfer the information to the fragment stage by calling Unity transfer instance ID. So now when you create a material that uses the shader we just created, we will have a field called enable GPU instancing. The problem is, or at least I encountered the problem, that the toggle doesn't do anything. And so instead we go to the debug inspector and we enter the keyword manually, which is called instancing on. So this is just a very basic instance shader, but it's good enough for now. And when we then want to render our meshes, we need to call graphics.render mesh primitives. And the reason we don't use draw mesh instanced is because draw mesh instanced is limited to 1023 instances per draw call, which you can of course call the function multiple times. But it's just easier to use render mesh primitives, especially because we are using graphics buffers already anyway. So whenever I create these tutorials, I usually create the scene and the code and the assets beforehand, and afterwards I talk about them. Sometimes I write the code, but in this case it's just like a few hundred lines of code, and the keyboard is quite loud. It doesn't make sense for me to write it again. And so you want to start simple. You want to create a fish swarm behavior, which you just attach to a game object in your scene. So just like this. And you just start with the instances, how many instances you want to draw. The material, which in this case is our instance material. And the mesh, which in my case is a fish, but it can be any mesh. And in order for us to call render mesh primitives actually, you will need render parameters. And you can just store them in a private variable, and when you initialize the script, you will also initialize the render parameters. And it has a lot of fields, but most of them are not important because the default values are quite alright actually. The only thing you need to be aware of is that you need to override the default bounds with some pretty high values, You can use the exact values, then you need to calculate them, or you can create just some very large bounds. The reason we have to do this is because we change the position not from the CPU, but from the GPU. That means the bounding box of all of the complete swarm is changing on the GPU, and you can send the correct bounds to the GPU, or you just make them very large so that it is not culling. Because if they are too small, then frustum culling will just make all the complete swarm disappear. And the other thing you need to provide is the fish material. And then later on, when you update, you want to call the functions with the render parameters, the mesh, the sub-mesh index, in my case it was just 0, and the number of instances. So your script will then look something like this. And the only thing I forgot is that because we haven't defined the matrices yet, we have to define some temporary matrix. I called it object to world, and we also have to define it in the shader, and then use it instead of the usual object to world matrix, because it's not defined with when you call render mesh primitives. And after you converted the object position to the world position, you just multiply with the regular view projection matrix. And now after these changes, you will see your mesh at the origin. It's actually then multiple meshes depending on how many instances you have. And so our next goal is to adjust the starting positions so that the fish spawn within a radius. So we can't do it with a single matrix we just defined. We need an array of matrices, which means we need a graphics buffer. We have thousands of objects to query each frame. Are they starting to affect your performance? Well, I have a solution for you. Gimme dots geometry. It has quad trees, it has octrees, it has KD trees, and a lot more stuff. It is all implemented in dots, buy now for just $25. So this is what the script looks like when we integrated the graphics buffer. I just added a job that calculates the matrices. You have to remember we have like more than 100,000 instances, so this can take quite a while if you just do it in regular C# code. And in the initialization, we we just call this job, schedule it, complete it directly, then create a graphics buffer, which is just a structured array on the GPU. With structured, I mean you have a certain stride with a certain byte size. And after we set the data, you can use native arrays, by the way. You set the buffer from the material, which is a special method, and that is basically all. So we initialize the data from the graphics buffer in the native array, and then we initialize the graphics buffer. We send the native array to the graphics buffer. We set the buffer to the material, so we bind them together, and that means the data is sent to the GPU, and it's now not our problem anymore from the CPU side. What you have to remember is after you destroy the object again, you have to release the graphics buffer again. Very important. So now we need to access the matrices from our shader code. First we remove the object to world matrix because we don't need it anymore. Then we add a structured buffer that holds our matrices, and we name it the same way as the name we used when we set the buffer in the material. So in my case this was fish swarm transforms. I usually have a file that holds all these strings, and then I convert it to IDs with a static constructor. Now we replace this object to world here with the fish swarm transform. And the way you access structured buffers is the same way as you would access an array. And we want each instance to get its own matrix. And the way you do it is to use the field Unity instance ID, which is just an identifier which is unique to each instance from this draw call. So you say fish swarm transforms, then we access it like an array and use Unity instance ID. That is all. Now each fish will get its own transform matrix. Unity will complain now because it does not know the field Unity instance ID, and this is because the field is only available if instancing is on. So we need to add the macro here, instancing on, and that will remove the error. So I just noticed that we actually never used this world position here. We never used the object to world matrix either. We just multiplied by the view projection matrix, so it doesn't matter in this case because we set the object to world matrix as the identity matrix, and that's why I didn't notice. But what you have to do is replace this with v.vertex. So I've made a very funny mistake. You see I'm using a parallel for job here, and I'm also using the random struct of the mathematics package, which means this is copied to each thread, which means it has the same seed, which means the numbers that are generated in each thread are the same. Which in turn means I've calculated all the matrices like 8 or 9 times in the same way, which means in turn I didn't render 100,000 fish. I did render 100,000 fish, but 8 of them were just in the same position all the time. Fixing it is pretty easy, you just make it to a single threaded job. Okay, so like this is 300,000 fish. Now that we don't overdraw each fish 8 or 9 times, actually the performance is a little better. It's a little bit better, so we can draw even more. And this is like an insane amount of fish. Like, look at this. It's like, I don't know. So now when you start the game, it should look something like this. Just a bunch of fish which are not shaded, spawning within a sphere. Now all that is left to do is to move these fish around, and like I said in the beginning, using just C# code would be not performant because we have 100,000 instances. So we will use a compute shader for that. Okay, so let's create our compute shader by create shader compute shader and call it move. You can reference compute shaders like any other asset files. So you can just do this and you will see a field in the inspector after we load it. And now we drag our move compute shader into this field. So when you use compute shaders, you should always create an instance of them at the start of the script, so that if you change the data, different scripts will not interfere with each other. So here we create a new instance, and we are not allowed to forget to delete it afterwards again. So let's take a look at our compute shader itself. We can delete all these comments, and we will rename this to move. And don't forget to rename the kernel as well. We don't write to a texture, and we can basically leave everything empty. We also don't have multiple dimensions, we only have the x direction essentially. So this is basically our starting point. So I want to quickly mention that we will not make as complicated of a compute shader as I showed you. We will just move around the swarm in a single blob. And the reason is it would take a long time to explain it, and also you can find the project files in the description below. So with that said, we need our swarm matrix, which is now the matrix of our swarm game object, which we will send to the compute shader later. And we also need a read-write structured buffer, which holds our matrices, which again is our fish swarm transforms. So this is again our graphics buffer. And the only difference between a read-write structured buffer and a structured buffer is that you can write to a read-write structured buffer. Now, how it should work in theory is we have our game object transform, and we want to add an offset to it where our fish is. So we need to provide this offset information to the compute shader, and the best way to do it is again to use another structured buffer, which means on the CPU side we need another graphics buffer. So because you will probably need a lot more data later, I will do this with a struct, and I call it fish data, and the only thing that's inside there for now is an offset, and then we create a structured buffer using this struct, which we call fish swarm data. So let's assume we already have sent the correct data, then all we do is first getting the fish data, which is indexed as so, and then we will add the offset to the local to world matrix, and then we assign it again to the fish swarm transform of this particular instance. And essentially we are doing an object to world transformation based on our swarm. I created another graphics buffer that will hold our fish data, and so we have our struct in the compute shader, which has an offset field which is a float 3. So it's 3 floats, meaning it's 12 bytes. And so the important thing whenever you want to transfer CPU data to the GPU is that the memory layout and memory size in total has to be the same. So in this case, what you usually do is you create a struct on the CPU that has the same memory layout as the struct on the GPU. So an example for this, how it would look like, is this. I use the float 3 of the mathematics package, but you can also use the vector 3. They all have 12 bytes, that's the important part. So the memory layout, the size of the struct is the same as on the GPU. And now we basically do the same strategy as before. So we have another native array. In this case, it's not matrices, but fish data. And we will later on fill this data in the job. And afterwards, we will create a graphics buffer and set our fish data to the buffer. Then we also transfer both graphics buffers in this case to our compute shader. And again, we're not allowed to forget to release the graphics buffer after we're done with it. Filling this struct is very easy as we already have calculated the offset. A compute shader is not executing automatically, so we have to call it. First we find the kernel we want to execute, then we calculate how many thread groups we need, and then we dispatch it. And you do this every frame for updating the positions. The only thing we haven't told the compute shader yet is the transform of the game object, and for that we just call set matrix, like so. And now when you start the game, you will notice that nothing is going to happen, and the fish are still where they were before. But if you move around our swarm game object, you will see that the fish are moving with it. And when you rotate it, each fish will rotate individually in the same direction. So that means what is left to do is actually very easy. We just need to move around the swarm object and let it follow the hook. So you add some variables like you usually do. You have the swarm speed, you have the swarm rotation speed, and you have the hook. And then you simply move them like you would in any other script. You just let the transform follow the hook. And that is all there is to moving around 100,000 objects. Of course, this is a very simple movement, and you can make it more complicated in the compute shader. And you can add some colors to the fish, and you can add some scale, and you can make them a little bit slower or a little bit faster. And yeah, you can have your fun with this. So of course I have to show 100,000, so it's pretty ridiculous. So thanks for watching. Leave a follow, leave a like, And you can find some links in the description. One is to the asset store, where you can find some products of mine, mostly shaders and crazy algorithms, because that's all I do. Then you can find a link to Patreon if you want to support me more directly, and you get some exclusive content there, and a link to the project files if you want to have a look at what we did in this tutorial yourself. And yeah, that is all. Bye.